Okay. Good morning and good afternoon, everyone. On our second day of CaRT conference, it's my great pleasure to introduce our first invited speaker of today's session, Professor Aleksandra Tepeh from the University of Maribor in Slovenia. She's working in the Institute of Mathematics and Physics at the Faculty of Electrical Engineering and Computer Science. And her research covers a lot of a wide variety of topics in graph theory, from Wiener index in the chemistry up to domination and rainbow domination. When I met Sandra, it was in Spain when we were in the staff week at the University of Cadiz. And we were together. We were included in the proposal that Hannah and others prepared in a grant of European grant. And exactly that day when we met, Sandra was late for our meeting at the university because of the funny story. Because a beard popped on her, and we say in Poland that it brings a good luck. And exactly that day, we received the information that our grant was accepted. So from then, I think Aleksandra is our talisman, and we have to include her every time where we want to apply for anything of any grant. So I hope also here she will be our talisman of our session. And like a rainbow, and she's an expert in rainbow domination. Like rainbow has a lot of colors. I think Sandra has also her whole spectrum of colors, from the calm, happiness, empathy, and the joy, and all the best. So I think now Sandra is going to talk us about the conjecture on induced cycle vertex number. She also includes the concept of 1-2 dominating set, but I think that it's the same name, but a little bit different definition as yesterday Ula taught us. So I think it's the same name for completely different concepts. So I'm really curious and I'm waiting for your talk. So please, Sandra, the floor is yours.
Thank you, Magda, for this very nice introduction. Everything holds, everything is true. So just let me share my slide. I hope you can see them. Yeah, everything is okay.
Okay. Yeah, everything is okay.
Okay. So you already said half of the things I wanted to say. I just wanted to warn you that this is not the same 1-2 domination, and we have to be careful when we are trying to search for the literature on the internet or everywhere else. So I will explain what this type of 1-2 domination is a little bit later. I would have to say that this is a joint work. I mean, this talk is based on joint work with my colleague, Ria Erves. And if somebody will be interested in that topic later, one can find all the information and all the details here in this paper that was published recently. Here you can see the informal title of my talk, which I like much more. So today I would like to tell you a tale of interesting creatures living in the kingdom of cubic graphs. And in this tale, I would like to present a thought process, how some initial ideas became a paper. So I will, of course, skip long proofs and harder ideas, but I will include some simple stuff. Yeah, so what are these creatures here? What do they have to do with my talk? Of course, I will talk about graphs that look very much like these creatures. These are trilobites. They're supposed to be the second most famous fossil group after the dinosaurs, but some more fun facts about those creatures a little bit later. So let's start at the beginning. We have to recall what is a regular graph. It is a graph where each vertex has the same degree, and if this degree is 3, we call such graph cubic graphs. We'll be only interested in cubic graphs today, and you can see some examples, very simple examples here with Peterson graph probably being the most famous one among them. Well, we have heard many times the definition of dominating set probably, but just in case, let me repeat it. So a set of vertices in a graph is a dominating set if every vertex is either in the set or is adjacent to a vertex in the set. So of course, this set of green vertices is dominating, but it's not really an interesting one because we are in domination, we are interested in the minimum size of a dominating set. And you have probably heard that domination concept origins from recreational mathematics. But in fact, already in the 4th century, some ideas from domination were used to defend Roman Empire. So maybe you have heard of a Roman domination, a special type of domination. And today we know this type, I mean, there are many types of domination and they are used in many areas. I have written just a few of them, but unfortunately I don't have time to tell you all the details. So I said we are interested in the minimum size of a dominating set. So for this graph, for instance, we see that this blue set of vertices is a dominating set. You can check that easily. So domination number is at most 3, but we can see that we can dominate this graph only with 2 vertices. Yeah, we cannot do it with 1 because if in that case we would need a universal vertex which is connected to every other vertex in the graph. So gamma of this graph is 2. Now, what is a total domination? Total domination number. Well, here we require that every vertex, not just those outside the set, but also those in the set, that they see a neighbor in the set. So these blue vertices, they are a total dominating set, but this set is not optimal in the sense of cardinality. We are again interested in the minimum size of a total dominating set, and we call this number the total domination number of a graph, and we can do it with 3 vertices, but not with, with 3 vertices, yeah, but not with 2, because in this case, these 2 vertices need to be adjacent, and if you can imagine any pair of adjacent vertices in this graph, you will easily see that one vertex is left undominated. Okay, now let's go to this stronger version of total domination that I learned about from this paper of Fakran and others. And you see that this type of domination, this type of dominating sets are defined for graphs where every vertex has degree at least 2. And we have this additional condition to that condition that we have in ordinary domination, where we say that every vertex must have a neighbor in the set, like in this case, in this set of red vertices, but also every vertex in the set, that is every red vertex, has at least 2 neighbors in the set. Yeah, and you can see that this is optimal again in the sense of cardinality. We call the minimum cardinality of a 1-2 dominating set the 1-2 domination number of this graph, and you can see that this is 4. You cannot do it with less, because if we would have 3 vertices in a 1-2 dominating set, they need to be connected one to each other. So they induce a triangle, and we have only 1 triangle here. But this graph, this triangle doesn't even dominate the whole graph. Yeah, so gamma 1-2 of G for this graph is 4. Okay, we can learn from this paper that this gamma 1-2 of G of any cubic graph of order n, this number is squeezed between half of the order of the graph and 3/4 of the order of the graph. And the authors proved that both bounds are sharp. Well, for the lower bound, they even characterized all the graphs which attain this bound, yeah? And they called this family of graphs that attain this lower bound, they denoted this family with the G cubic. And graphs in this family can be constructed in the following way. We start with a two regular graph, like this union of these two blue cycles, and then you add another union of cycles on the same number of edges. So we have we have 9 blue edges, blue vertices, sorry, and 9 red vertices, and then we put matching, perfect matching between them. Yeah, something like this. This is one example of a graph which is in G cubic. So all the graphs look something like that. What about the upper bound? Well, the authors found graphs which attain the upper bound. This is one nice example of a nice graph with a nice name. This is so-called diamond necklace, because you can see here these 6 little diamonds. And the family of diamonds, shorter, longer, is a family of graphs for which this bound is attained. And I found characterization of graphs which attain the upper bound interesting, as interesting question. And then I showed this problem to my colleague, to Ria. And then we started to ask ourselves, how can 1-to dominating sets look like? And we were drawing some pictures, and of course, first we found out that sometimes 1-to dominating sets, they induce cycles. This is not always the case. So if now I draw the induced cycles, induced subgraphs, which are induced with these red vertices, then you will see that in this case, I have 1 cycle, here I have 2 cycles, but this is not necessarily the case. It need not be a cycle. But anyway, we were interested, is there anything known about induced cycles in cubic graphs? So we were searching through the literature, and then we found these 2 papers. Yeah. So in these 2 papers, we found out that the problem of finding the largest induced or regular subgraph within a given graph is a problem that dates back to Erdős. And now you can see that if instead of R, we put in 0 or 1, then this is exactly the problem of finding a maximum independent set, or the problem of finding a maximum induced matching, respectively. But nothing was known up to this point for R equal to 2 or bigger. Okay, so in this paper, in this first paper, they introduced this notion of the induced cycles vertex number, which is denoted as CIND, which is defined as the maximum number of vertices in G that induce a 2 regular subgraph. So I can say equivalently that we are interested in the cardinality of the largest set of vertices that induces 1 or more cycles. So we can take a look at this example. So what is CIND of this graph? Well, we can see that this graph has somewhat tree-like structure, so we won't get any cycles here. All the cycles are there in the periphery. Yes, so I see 1 5 cycle here, but it is not induced. So the largest cycle that is induced here is this 4 cycle or this 4 cycle. So we get something like this. Yeah, this is one possibility. And it is quite soon clear that CIND of G of this graph is 24. Okay, now that we know what CIND means, we can take a look what is known for this graph parameter. In the papers I showed you before, the authors, they found the lower bound for general or regular graphs. And this lower bound in the case of cubic graphs simplifies to n plus 2 over 4. And they also examined some special families of cubic graphs, claw-free and four-chordal, and they obtained some bounds. This is not really that much important for our talk today, but I just mentioned these two special families of cubic graphs because they support this conjecture. And this conjecture is the conjecture that caught our attention again. So this conjecture says that if G is a cubic graph of order n, then this CIND of G is at least half of the order. Yeah, and these two families, they support this conjecture. And also, you can see one graph here, and this graph tells us that this bound is sharp. So, I mean, if this bound holds, it is sharp, yeah? Okay, so then we asked ourselves, what about the upper bound? And we couldn't find it for cubic graphs. So then Ria showed this example that CIND of G is at most 3/4 of n. And pay attention, this bound is the same as for gamma 1, 2, as we saw before. Yeah? And because this is not hard to see, we can quickly see that. I will show you the proof. To follow more easily, you can take a look at this picture as we go through this proof. So we will start with S, which induces a two regular subgraph, and this has it has maximum cardinality between all such two regular subgraphs. So cardinality of S is CIND. But because this graph is cubic and we already have for each vertex two edges going out of it, yeah? So we know that each vertex of S has exactly one neighbor in the complement, these black vertices. Moreover, we can see, because graph is cubic, that at most three blue edges, three blue vertices can share a common neighbor. So what do we get from this? We immediately get that the cardinality of the open neighborhood, yeah, these are these black vertices here, the cardinality of this open neighborhood is at least cardinality of S over 3, yeah? And from this we get this chain of inequalities. So N is, of course, at least the cardinality of the closed neighborhood. That means blue plus black vertices, and from this inequality obtain this, and we have our result. Okay, what about the graphs that attain this equality? We showed that, we characterized such graphs, and I will explain how their structure looks like. We start with a two regular subgraph, with the two regular graph, that is a union of disjoint union of cycles on exactly 3 k vertices. Yeah, k in this case is 3. And then we add exactly k vertices which are not connected to each other. So this is, I just added edgeless graph nk, and then we add edges so that we get a cubic graph, something like this. And if a graph can be constructed in this way, we say that G belongs to this family gamma. And these are exactly the graphs for which this bound is attained. How can we see that? Well, of course, if G has such a structure, then CIND is at least 3K. Yeah, these are these black vertices. Okay, so this is clear, and the opposite inequality we see here, so equality holds. What about in the other direction? Well, we will assume that C, I, and D is exactly 3/4 of n. And of course, because this number is integer, n must be divisible by 4. And let S be a two-regular subgraph, which attains, whose cardinality is C, I, and D. So this is 3K, of course. And now we take a look at the remaining edges. Well, we have exactly 3K edges already in the subgraph induced by S. So we are left with 3K edges. And because every, let's say here, black vertex has to have a neighbor outside this two regular subgraph, we know that there are exactly 3K edges between vertices of S and between vertices of the complement of S. But there can be no more edges because the number of edges in cubic graphs is 3n over 2, which is exactly 6K. So there are no edges between vertices in the complement. So this means that graph for which this holds, this equality holds, must have such a structure. Okay, now when Ria showed this, her bound, what she proved, I was thinking, is there any connection between gamma 1, 2 of G and Ci and D? I mean, these numbers are the same, yeah? This is the conjecture, Ci and D is supposed to be greater than n over 2, but is there any connection? I mean, that would be pretty awesome if we could show that this inequality holds, because that would mean that also Mike's conjecture holds, yeah? So that was the motivation why we started exploring this relationship. And well, we observed pretty soon, let me just show you the picture. We observed pretty soon that as soon as we find a two regular subgraph like this blue one here, such that the closed neighborhood of the vertices in this subgraph is the whole vertex set, which is the case here, then this inequality will hold, right? And we were drawing many examples, and this appeared actually all the times at that point, yeah? So we had these inequalities. So we said we have to start to think about this more systematically. Okay, in this case, we have this inequality, and does this hold always, or what is it with this? So we started more systematically. We started with cases, small cases, and this holds for n equal to 4 and to 6. And then we obtained some sufficient conditions. So if C and D is this number, or if cardinality of the vertex set is at least 8 and C and D is this number, then this red inequality holds. It also holds, and we showed this by using these two previous results, that for every cubic graphs on at most 8 vertices, this red inequality holds again, and also in this case. So we knew that if we want to find a counterexample, a graph for which the opposite inequality holds, then this graph should have at least 10 vertices. And after quite some effort, we found one. Yeah, this is the smallest possible trilobite. Yeah, I will explain how the other trilobites look like. Because later we were able to find, actually for every n, we found one graph. Yeah, how do these graphs look like? First of all, I will explain how do we get trilobites on 12, 16, 20, and so on vertices. So this number is, if n is divisible by 4, then our trilobite is a graph that can be obtained from from 3 disjoint paths. We start here with 3, then with 4. If n is 20, these paths would be paths on 5 vertices. And then we connect these upper vertices so that we get a triangle. And for the lower part, we add another vertex and connect it to these other ends of this path. And we add another such vertex. So here you see these vertices, they induce K23. Yeah, so this is always the case for every trilobite on the number of vertices which is divisible by 4. Of course, this is not a cubic graph yet, but you add for the rest of them, for the vertices that belong to the same layer, as we call them. These are the vertices which are drawn here on the same height. You add one additional vertex and connect it to these 3 in this layer. So here you get a claw. Yeah, so bigger trilobites will have more claws. That's the only difference. And for the rest, if n is not divisible by 4, then we obtain trilobites like this. Also, in the beginning, I mean, you add here these 2 vertices to obtain K23, and K23 again to obtain this lower part. And all other layers, so we call this first layer and this is the last layer, and all other layers are just induced claws. Okay, so this is how trilobites look like. Maybe you already see the resemblance with the creatures I showed you before. This is just to show you maybe an example how do we get a trilobite on 22 vertices from a trilobite on 18 vertices. We just add this orange claw here, yeah, and you can see here some longer trilobite, yeah, with its gamma 1,2 set, these bold edges. If you take a look at them, this is the optimal gamma 1,2 set. Well, it was a challenge to prove that Cind of t is n over 2 plus 1, and that gamma 2 is n over 2 plus 2. So gamma 1,2 is for 1 bigger than Cind, so we have the opposite inequality. Yeah, this red inequality. And I don't know, are there any other graphs with which satisfy this inequality? And we were trying to find them. We couldn't. Then we tested. We started to believe trilobites are the only graphs with this property, so that this inequality holds. And then we just checked our conjecture that there are no other graphs with computer. And well, then when computer said there are no other graphs, then we were brave enough to pose this conjecture. Actually, we have to conjecture. This is the stronger one, that there are no other graphs except for trilobites that for which this inequality holds. But it would be, for a start, it would be very good to prove that if G satisfies this inequality, so if Cind of G is at least this number, then we have this type of inequality here. Okay, so to sum up, actually, you already know why I like trilobites so much, because for them, it holds that Cind is greater than n over 2. But also, if this conjecture denoted with a star holds, then also that original conjecture of Mike holds. Yeah, Cind is greater than 2 n over 2. So yeah, this is what we are working on. maybe somebody can join us. What I would like to tell you at the end is just that we examined more graphs, of course, and in another paper with Gordana and Goran Radic, we examined this family of flower snarks. I won't go into details here, but I will just explain why we started to examine this family, because if you ignore these blue edges here, you can see that the graph, which is left, looks locally like trilobites. So if you remove their heads and their little butts, you get the structure as in flower snarks without these blue edges. Yeah. So for this family of graphs, we also showed what is gamma 1, 2, and this is less than 3K. So this family of graphs supports our conjecture. Yeah. So finally, just let me explain why the name trilobites, but probably I don't have to explain because they say picture says more than 1,000 words, and probably now you see the resemblance. Just some fun fact, trilobite, this literally means three-lobed entity. And I'm pretty sure that you can see this cephalon, this head here, and in this anatomy of trilobites, you can see thorax, this middle part, yeah, and this little butt here. And yeah, I was asking everybody around me, because I was drawing many such pictures, what do these creatures look like? This is some kind of animals or something like that. And everybody was saying worms and snakes and caterpillars or something like that. And I said, no, this is something else. And then I remembered these creatures that we learned about in primary school. And I said, yes, these are exactly trilobites. And you see some fun facts about them. So thank you. Just finally, another fun fact. I found this postal stamp of Slovenia from 2001. This trilobite was found in Slovenia in Karavanke region, but this is not 80 euros as we have them today. This was in 2001. We still had dollars back then, so that would be pretty expensive postmark, or what is the word today. So thank you very much.
Thank you very much, Sandra, for your very nice and interesting talk. As we can see, Sandra can join not only chemistry with the graph theory, but also archaeology and biology and with graph
Just
theory.
with the name.
Yes, of course. So, so now it's time for questions. Are there any questions? Yes, Julian. I see Julian. I don't know if.
Thank you. It was a really nice talk, and I really love the trilobite.
Thank you.
Yes.
I was wondering if you have thought about when you work with the flower snarks, there are like another two or three families like the Goldberg snarks that has similar structure. There is not
Yes,
claw,
we
but
did.
they can
Yes.
also work. I think maybe some of the ideas.
Yes, actually, my student is working on it right now.
So cool, so cool. And so
Yeah,
Planus a type
yeah, the
one or
topic is
two.
taken.
Yeah, that's cool.
Yeah, but it was yes, it is a natural thing to think of this Goldberg snarks. Yeah, yeah. Thank you for the question.
Thank you.
Any other questions? Maybe on. I don't know. We are online or not? We have any questions on YouTube or Facebook? Yeah. Oh, Rita has a question. Please.
I don't have a question.
No?
No, I only like to say thank you, Aleksandra, for your very, very nice talk.
Thank you for inviting me. It was a pleasure.
I think this talk is exactly that we like in our CaRT. It's a talk where we can understand a new concept for some of us, and we can. It's very nice show to our students how we work. Yes.
Yes.
Sometimes.
This was my plan, to show you the ideas and how
Yes.
things, how they are put together in unexpected ways sometimes.
Yes. Because sometimes I think, we think that everything is magic, but it's not magic. Yes, it's to think and to look. So thank you very much.
Sometimes we can be dinosaurs, like dinosaurs also.
Yes.
I have a question, Sandra, because you are thinking now about this cubic graphs. Have you thought about some generalization for regular graphs or other classes of graphs?
No,
about this parameter,
I haven't
how to
thought
compare
about
this
it
parameter?
Yet. No, I haven't thought about it yet. It is one of my questions, of course, but we are now into rainbow domination again.
Yes, I know. Yes, again.
So many ideas and not enough time to work on everything. But yeah, that is certainly a good direction.
Okay, thank you.
Thank you again.
Thank you again. So, if there is no more questions, I think we can say thanks to Sandra again and send her some. Wait. Okay. Everybody has to send. Yes, have to practice. Thank you. And I think we start in 3 minutes, Rita. Immediately.
Yes, I think we can take 5 minutes to start.
5 minutes. Okay.
Yes?
We can take 5 minutes break and then we can start with the next invited speaker. Thank you.
Yes.